In this video, we're going to look at an impact example. So what's happening in this picture is we have here a block that's hanging from the roof with two cables. And here we have a ball, A, that's hitting block B, and then the block B is swinging upwards. And so there'd be some sort of delta H here because the length of these cables isn't changing. So we have a mass of A here is 2 kilograms. We have a mass B here of 20 kilograms. And the question tells us that the force of A onto B takes 0.005 seconds. So we have a delta T. And we also have here an E value for our coefficient of restitution. And the question is asking us to find the average impact force exerted on the block during this time. So for this question, the first thing to notice is that we do have conservation of momentum, because here we don't have any external forces. So we have here the ball A has some linear momentum. It's going to be transferring some of that momentum to B, and it's going to keep some of the momentum for itself, but there's no external forces to that motion. So we have conservation of momentum. So that means conservation of momentum, the formula is summation of mv1 is equal to the summation of mv2. So in this problem, what that looks like is MAVA plus MBVB is equal to MAVA prime plus MBVB prime. Now sometimes you'll notice for that second moment, sometimes it uses prime, and that's the notation on the formula sheet for a coefficient of restitution. If you called this VA2 and VB2, that would be absolutely fine as well. So this gives us our first equation. We know our masses and our velocities, so this actually reduces, we know our initial velocities, and we know that initial velocity VB would be 0. We know the mass here is 2, and then this would be 2, and this would be 20. So that equation becomes 2 VA prime, So this equation becomes 2 times 4, 2 times 4 plus 0 is equal to 2 VA prime plus 20 VB prime. So that's that first equation. So that's the conservation of momentum. Now we're going to use our equation that uses this information from the coefficient of restitution. And that equation is E is equal to VB prime minus VA prime divided by VA minus VB. So this is the formula on your formula sheet. Now if I fill this in, we have 0.8 is equal to VB prime minus VA prime divided by VA, which is 4, minus 0, which is our VB. So this gives us a second equation. Now we know VB prime minus VA prime is equal to 3.2. Here we have two equations with the same two unknowns, our two velocities, and we've solved right away that our VA prime is equal to negative 2.54 meters per second, and our VB prime is equal to 0.654 meters per second. So what does this tell us? Well, this negative here is telling us that VA after impact is going to bounce backwards. VB is going to be moving forward because it's a positive number here. And I forgot to write my positive directions here. So now we know our velocities, but the question was asking us for the average impact force. So now to capture that force, we have to draw our diagram. So I'm going to scroll up. Now for this problem, you could draw it on the ball or the block. Both would work, but I'm going to draw the block. So here we have the initial linear momentum of our block here was MBVB, which is equal to 0. Now we draw the impulse. So the impulses are all the forces that are acting on our block multiplied by time. So here we have T in the cable times delta T, and we have another cable times T delta T. We have a weight down, the weight of B delta T, and we have that impact force from the ball onto the block. This is going to be equal to the MB VB after impact. Now this is really important. Even though, and I'm going to scroll upwards for a second. Okay, so the velocity of this block is not going to be exactly to the right. It's going to be sort of diagonal here because it's constrained by the length of these ropes. That is true. But immediately after impact, that initial moment, the velocity of block B is going to be just moving to the right. So we're not going to consider that diagonal motion right now. We're just looking immediately after impact. It's going to be moving exactly to the right. So that's why in our drawing, I'm going to scroll up again. In the drawing here, mass of B times velocity B is moving to the right because immediately after impact, that's what's happening. Now, to solve for the impact force, we can just look in the x direction because remember we have velocities here, so we can break them into scalar components. So in the x direction, we have 0 because the linear momentum at that first moment was equal to 0, plus the impact from the ball, so the impulse due to the ball, is equal to MBVB. Now we know, sorry, I should say VB prime here. So now we can say our impulse from the ball is equal to MB, which was 20, times VB, which was 0.654, and the impulse is equal to 13.09 Newton seconds. Just a quick note here, when I did the tension here, T delta T, these are two different ropes. The tensions aren't necessarily the same. They'd be slightly different, but in a problem like this, you can assume that they're the same. We didn't end up solving for them. It wasn't necessary in this case, but just a note there about that. Now, if we look at what the question was asking, and I'm going to scroll up again, the question was asking us to find the average impact force. So it wasn't asking us for the impulse of the ball on B, it wants the actual force. And we know the delta T here, so we have one more step until we're finished. Here, the impulse is 13.09. The impulse is equal to the force times delta T. Therefore, our force is equal to 13.09 Newton seconds divided by 0.005 seconds, which gives us 2,618 newtons. This is the impact force. It's quite a large number because it's impacting for such a short time. This also helps you see why sometimes we ignore the weight of a block or the force due to a spring because these impact forces are so big. So that's the type of question you might see for impact.